All right, welcome to the next video where we're going to be looking at specifically in a little bit more detail how we can do some of these tests to quantify what type of organic material we have in front of us. So the first thing is we're going to be looking at hydrocarbons. Remember we said that hydrocarbons are predominantly made of carbon, hydrogen, nitrogen, oxygen, and maybe some sulfur as well, depending upon what type of organic molecule. So, enzymes contain those. Amino acids contain a majority of those as well. Amino acids contain pretty much nearly all of them, depending upon the type of amino acid we're talking about. So we've done the char test, we've determined that it's organic. Now we're going to work out, is it a hydrocarbon or for, let's say, an alcohol. Well, we said that with hydrocarbons, they're insoluble, right? They're insoluble in water, and we know that from previous experience because the hydrocarbons, if I draw an ethane here, we have an equal distribution of electrons around our structure, and so therefore, since it's an equal distribution of electrons, we don't have a charge separation, and so we have only dispersion forces between one ethene molecule and the next. If we're talking about butane, propane, octane, we've only got dispersion forces, and so this is an hydrophobic. It doesn't like to dissolve in water, and so it's insoluble in water. Okay, and so really, if you remember back, we have two separate layers here. We have an organic layer and an inorganic layer, and that tells us that we have a hydrocarbon. Okay, so we're going to be looking at alkanes and alkenes. We're not going to worry about alkynes. We know that alkanes are single bonds, so I'll just do this, and then alkenes are double bonds. Okay, how can we tell the difference between those? Well, we've done that previously in the course, and we've said that we can determine them based on the bromine water test or the bromine liquid test, right? So in other words, we put a sample of bromine into an alkane and into an alkene. If it decolorizes rapidly in the dark, then that's telling it's alkene because it's undergone an addition reaction to the double bond. So that's why I've got down here bromine is in the dark. If we test it in the light, we'll have a rapid decolorization with the alkene. There will be a slow decolorization with the alkane because the UV light causes a substitution reaction to happen. So I'm just going to say down here that's dark, right? So that tells us straight away if we have a decolorization reaction occurring, then it's going to be an alkene, not an alkane, right? Is only for alkenes. The rapid decolorization occurs for that, not for that. What about its reaction with sodium metal? Well, it doesn't react with sodium metal, so no reaction. Okay. What about solubility in water? Well, we said before that they are insoluble in water. What about its reaction with carbonate? Well, there's no reaction, right? So there's no CO2 gas produced. So from these distinguishing tests down the bottom, we've worked out that our sample is organic because it's charred. Okay, cool. Well, what about if it reacts with bromine water? Cool. If it reacts with bromine water, we know it's an alkene. If it doesn't react with bromine water in the dark, it's an alkane. But it also could be other organic compounds. It could be, let's say, an acid. An acid does not react with bromine water. So let's look at now some different other tests you can do with the different classes, and then we'll do a summary of all of them, and we'll see how you can use that summary to systematically determine if a sample is, once you've said it's organic, if it is an alkane, alkene, alcohol or acid. So copy all that down. I'm going to rub out the bits and pieces, and we're going to look at alcohols next. All right, now let's look at some alcohols or alkanols. They're predominantly carbon and hydrogen and oxygen. Okay, they are soluble in water. Why? Because they've got the OH functional group. So if we write that there like this, then that functional group there, the OH or the hydroxyl functional group, that makes it water soluble because of hydrogen bonding. What other aspects can we think of? Well, let's draw an example here. If we have one that we're all familiar with, ethanol. Okay. So ethanol has the OH group, so therefore it's soluble in water. Now, The longer the carbon chain, then the more insoluble it's going to become, right? So if we only have one OH group, when we start increasing the length of the carbon chain there, it's going to become more and more insoluble because this portion of the molecule is hydrophobic. And that's why, if you remember when earlier on in the course, this section here was good at dissolving non-polar substances and this was good at dissolving polar substances. So that's why ethanol is considered the universal solvent. But if we increase the length of that carbon chain there, then it becomes insoluble. So when we're saying soluble in water, it's usually for the small molecular mass alkanols. Now, what about these down here? Well, does it react with sodium? Yes, it does. It reacts with sodium to produce hydrogen gas. Okay, so straight away, in comparing what we just previously talked about, the hydrocarbons, if you had a sample of hydrocarbon and a sample of alkanol, and you wanted to test which is which, well, you could do the bromine water test, and let's say both of them did not react with the bromine water test in the dark. Well, that's telling you a little bit, but not the full story, because we know that alkenes react, but alkanes don't. So we could still have an alkane and an acid now, sorry, an alkane and an alcohol. But if we put sodium into both samples, sodium reacts with alcohols, but doesn't react with the alkane. So now we have a distinguishing test which can tell us the difference between an alcohol and a hydrocarbons that is an alkane. Okay, bromine water test. It does a little bit slowly, right? So that slowly aspect is getting closer to not telling us really that much, because we know that alkanes slowly react with it as well. So the better test would be the sodium test to distinguish between an alkane and an alkanol. What about water? Well, we said before that it is soluble in water, and when it's soluble, it's non-acidic, right? So that's going to come important when we test acids, obviously. So it's non-acidic, soluble and non-acidic. What about carbonates? Well, it does not react with carbonate. So there's some of the tests and the results that you can do with alkanols. Get those down, and then we're going to draw up one for an acid and see how that's different, and then we'll summarize it all together, right? See you in a sec. All right, now we're back. Now we're going to be looking at acids, okay, and in organic chemistry we call them alkanoic acids. They're composed of carbon and, whoops, I was going to write nitrogen, carbon and oxygen. There we go. It's got a functional group here, and the functional group is the carboxylic acid group. So we'll just draw it here. Okay. And with the carboxylic acid group, this portion of it is called the carbonyl. Okay, the carbonyl group. And we'll find that that's important with ketones and aldehydes later on, but it also contributes quite significantly to its bonding. So we have the carboxylic acid group, which is all of it. Okay, and when we talk about bonding with carboxylic acid groups, we really want to be talking about how it can form dimers, right? So we have a delta minus up the top here and a delta positive. The oxygen's more electronegative than the hydrogen and the carbon, and so it's going to tend to keep more electrons towards it, which means this is going to be delta positive. And so that means that if we have another carboxylic acid group, then that there can bond with the delta positive hydrogen, and the oxygen, the carbonyl oxygen, which is delta negative, can form a hydrogen bond with the hydrogen there. And so this here is called a dimer formation, and so carboxylic acids will have a higher boiling point than correspondingly the same molecular mass of or similar molecular mass of alcohols. So if we had, let's say we had butanol or butanol and butanoic acid, then even though butanol can form hydrogen bondings, there's only one H bond per molecule. Here we have two, the dimer formation, so therefore it's stronger, so you'd expect butanoic acid to have a higher boiling point than butanol. Okay, so the functional group there is with the acids. Do acids react with sodium? Well, let's go through the reactions here. I might just draw an example out. 1, 2, 3, 4, so that's going to be butanoic acid. And so with acids, they do react with sodium to produce hydrogen gas. They don't react with bromine water. So going back, if we had an unknown and you test it with bromine water and it didn't react, that's telling you that it's not an alkene, but it doesn't tell you whether it's an alkane or an alcohol or an acid. So remember we said before sodium could react with an alcohol. Good. So we can get rid of the alkane. But sodium also reacts with the acid. So at the moment, giving it some metal doesn't distinguish between an alcohol and an acid yet. So we've got to get another test to distinguish between that. What about water? Well, it is soluble in water, but it's acidic. So in other words, we can dissolve it in water and test the pH. If the pH is low, then it is an acid. Remember with an alcohol, it was not acidic. So we dissolve it in water and it's not acidic, and therefore we could say therefore it's an alcohol. What about reaction with a carbonate? Yes, it does, and it produces CO2 gas. So we can see here that, oh, lost the pen. Here we can see here that with an acid group, the metal test does not help us distinguish between an alcohol and an acid. Neither does the bromine water, but these two do, right? Specifically the carbonate, okay? Because alcohols don't react with carbonate. So let's now put a summary table up, put all the features down, and it will become clearer how we can use those tests, those lab tests in the school lab, to distinguish between our organic materials, right? Get this down, I'll see you in a sec. All right, now let's put it all together and see how that makes sense, right? So let's just take it back.
Come on and take it back, love.
To the fundamental idea. You've got a sample here in the lab. In the school lab, you've got an unknown colourless sample. What is it? Well, we've done the char test. We've determined that it is organic, but which group of organic material does it belong to? So we have these distinguishing tests here. So with an alkane does not react with sodium. Well, an alkene does not react with sodium. So if we react it with sodium, we can't distinguish between those two there, right? Both of these do react with sodium. Okay, so let's say you got the sample, it doesn't react with sodium. We're down to here now. What about the bromine water test in the dark? Well, in the dark, an alkane has no reaction, or it's because it's undergoing a substitution reaction and it needs UV light. Since it's in the dark, there's no UV light, and therefore it doesn't undergo any colour change. But the alkene does. So straight away, you can use that test to determine between whether it's an alkane or an alkene. But what about alcohols? Well, alcohols, we said, in the dark, very slow. So if it does react, we've got a fast reaction here. We've got a slow reaction there. We want to make sure, be a bit more definitive, that we can determine the difference between an alkene and an alcohol. Well, let's look at something else. Let's look at maybe solubility and acidity of the water. Well, both of these are insoluble, so they don't dissolve into polar solvents, and they don't react with carbonates. So if we have determined that they are insoluble, right, because alcohols and acids are both soluble, right, and they both react with metals. So if we find that they don't react with sodium metal, they're not soluble, and then we can say it's either down to these two. The distinguishing test you would use would be the bromine water test. Okay. What about alcohols? Well, we said that alcohols react with sodium, and so does acids. Well, they slowly react, and the acids don't react with bromine water. So once again, you want to think, well, I want something a little bit more definitive than that. They both are soluble in water. However, this is releasing a H+, and therefore the pH is low, right? So we've got a low pH. So we could use an acid-base indicator or a pH probe. So we get two of these samples. Yes, they both react with sodium. Great. They're both soluble, but let's just test the pH. The pH is low, looking like it's an acid now. What about reaction with carbonates? Yes, it does. So if we do the carbonate test and it produces gas, it has a low pH. then that's telling us that it's pretty much an acid. Okay, so there's the summary of the tests there that you could use in the school lab to distinguish between these compounds. In the forensic lab, of course, you need to use machines that are a lot faster, more efficient, and are more precise in distinguishing between these compounds. But that's for another video. So hopefully everything makes sense there. Get it all down, and I hope you have good fun in the lab working out your unknowns. See you in the next video.